So, what else we need to know about Chapter 3? Well, temperature measuring devices. Thermometers, right? So I brought your typical thermometer. Old-timies, we used to use mercury in the bulb, but now it's like alcohol. Thank goodness, right? But basically, we talked about when you heat something up, it goes faster, and as it goes faster, it expands. And so actually, as you heat this up, the liquid in the bulb expands and it rises up. Okay, so that is a liquid in glass thermometer. I don't have an example of this one, but I do have a figure from your textbook. And it kind of goes back to like a liquid expands. Well, metal also expands when it's heated, and maybe you guys already know that. And different metals will expand at different rates. So what you're going to see here in this figure basically is a couple of metals. One expands more than the other, and it basically makes this kind of flexing thing. Remember a minute ago I told you that if you want to know the temperature, you can basically have this tub thing moving and this pen kind of moving up as this tub moves around. That's the type of thermometer that could do that. And then another one, actually this one is the most rugged. Where did it go? Okay. So in the chem lab, we can plug this into a box or a receiver. But this is this thermistor, okay, or thermal resistor. Basically, the electrical conductivity, how electrons will flow down that, actually kind of flow through this, is affected by temperature. Okay, so I'm pretty sure this is how it goes. The warmer it is, the easier it flows, the more conductive that metal is. As it gets cold, the electrons move more slowly. The conductance is less. So basically it translates, the box that this is connected to measures the conductivity, and it translates it to a temperature. So these are actually what you see in those automated things that are by airports. Those ASOSs will have this sort of device because it's a lot more rugged than this device. Okay, which isn't really a device, I guess. So thermometers, you can actually do a few things with them. It's kind of neat. This is your normal thermometer over there on the left. But if you kind of, this one right here, oops, where'd it go? This top one in the middle, okay? If you have like kind of a little kink here, like a restricted place, you can actually you can capture the maximum temperature, okay? And then reset it later. So basically, say it swells, okay? It gets hot, it swells, okay? And it reaches a maximum. What if it cools back down again? Well, if there's this extra little thingy right there, okay, it's in the thermometer, it's going to stay up there, but the other's going to fall back down. Now you can reset it, but that will capture the high temperature. This one, similarly, actually will capture the low temperature. Kind of a different gizmo there, they have a little floating thingy there to kind of capture the minimum temperature. And this is your two metals right here, a bi as in two metal strip, that actually, depending upon the temperature, this curvature will change. And as it changes, it ultimately moves this thing up or down. And then this is kind of like the little barrel thing that, I worked at the ammunition plant for many years, and out there in the factory, out in just plants in general, if you want to know what the temperature is, over the course of 7 days, you just stick one of these things out there. But don't forget to wind it, okay, so that it will turn, and don't forget to make sure you tear the sheet off so it doesn't like rot over itself, because then be like, I don't know what day that was. Okay. So this would be the conductivity thing, okay, kind of hidden in there. And like I said, these are just set to be kind of really automated. So, speaking of those ASOSs, just to kind of, when I say ASOS, it's an acronym, ASOS. And we ran into that on a previous slide. Basically, automated surface observing system. So not only measuring temperature, but also measuring humidity, wind speed, wind direction, cloud ceiling, and a lot of times, like I said, these are near airports. But this one is measuring temperature. And of course they go with white. These things are always going to be white. On my list of things, like I think I told you guys, is to kind of swing by, as I'm going to Burlington, the airport, kind of just, I think I've seen it before. Maybe I'll take my camera and see if they'll wonder why I'm taking a picture of their ASOS. Okay. So just a little bit about temperature scales. So temperature is an indication of motion or kinetic energy. Now, temperature is only one indication of thermal energy, because you got to know how much stuff there is to ultimately tell thermal energy. You also need to know the specific heat of the object to kind of narrow down on the thermal energy. But temperature scales, the two that, the one we're most familiar with when it comes to weather is probably Fahrenheit, degrees Fahrenheit. But here in North America, we've kind of been stubborn to move to the metric system, and Celsius is a metric temperature. So one of these days. And Celsius is so beautiful because, like, with regard to water, you know, water freezes at 0 degrees Celsius, 32 Fahrenheit, and it boils at 100 degrees Celsius, 212 Fahrenheit. Now, which of those are a prettier number? Okay, set of numbers, of course, it's that one. So the Celsius is metric, and actually kind of related to the Celsius is the Kelvin scale, which I'm going to talk about here in a minute. Now, I don't have any problems with you guys going back and forth between the Celsius and the Fahrenheit scale. I figure you guys can look it up, but the way this works is if you have the Celsius temperature, if you have the Celsius temperature and you want Fahrenheit, basically you plug the Celsius temperature in there, multiply it by 1.8, add 32, and that will give you Fahrenheit. And in this one, if you have the Fahrenheit but you want the Celsius, you plug your Fahrenheit in there, subtract 32, divide by 1.8, and that'll give you Celsius. Okay, so again, Celsius is the whole metric thing. But Celsius isn't the coolest, no pun intended, coolest scale. Actually related to Celsius is the Kelvin scale. And this goes back to, remember, all matter has motion basically, and the warmer it is, the more motion it has, and the cooler it is, the less motion it has. Well, you're like, okay, dude, what if it has no motion? And that would correspond to a temperature of absolute 0, no motion. But if it has no motion, it has violated one of the tenets of matter, which is all matter has motion. Okay? So it's like, what do you do? Well, as far as I know, 0 Kelvin, 0 Kelvin, absolute 0 has not been attained. I think it was like in the news, somebody said, yeah, we went colder than absolute 0, but what it was kind of like a distribution, like a bell curve of temperatures, and it just kind of slurped over into the... So, Celsius is metric, Kelvin is metric. And so what they did, and it kind of makes sense, is the units are the same. So 1 unit on the Celsius scale is the same thing as 1 unit on the Kelvin scale. But you're like, well, 0 Celsius, that's like freezing point temperature of water. You know you can have negative Celsius. We have it all the time, right? So what they did was basically match, or how it works, I guess I should say, if you go down to negative 273 degrees Celsius, you are at 0 Kelvin. 0 Kelvin, and it steps up from that. So, in other words, if you go negative 273 degrees Celsius, if you go up to 0, and you take your Kelvin scale and you go up to 0 Celsius, you are at positive 273 Kelvin, because that's kind of how that works. So 0 degrees Celsius is equal to 273 Kelvin. So if you want to go back and forth between these two, it's not too bad. Basically, if you have the Celsius scale and you want Kelvin, then you add 273. If you have the Kelvin value and you want Celsius, you subtract 273. I know it says 273.15 here, but something I was going to say. It must not have been too important. Okay. Right. Oh, I know what I was going to say. Okay. And I can say it here too. So here's the 3 temperature scales. We have the Fahrenheit, which is what we North American people like to look at the temperature of this. Because I mean, I wouldn't, if somebody said it's, let's find something. If somebody said like it's, let's see, about 85. Somebody said it's 85 outside, of like, oh, that's wonderful. But if they said the corresponding temperature like was like maybe 29 Celsius, I'd be like, I have no idea what that means to me. Okay? But my husband pointed this out, that I think we got it going on, really, with our Fahrenheit scale, because we have more divisions, you know? Celsius, you'd have to be starting to use fractions to make it sense. So, because there's a big difference between 80 and 85, I think, you know? Let's see. So, right down here. So the third one is the Kelvin scale. So I'm going to, if we kind of extend that down there, we said absolute 0, okay, is 0 Kelvin, and it is negative 273 degrees Celsius, right? Negative 273.15 degrees Celsius. No joke. So this summer, twice we have gone to Chicago. We took the train there. It's kind of a nice little day trip. And we went to the Adler Planetarium. The Adler Planetarium has some great exhibits. It's awesome. It has like a series for planets. It like has a little thing for each planet. If you go look at each planet, they will tell you the temperature of the planet, the surface temperature of the planet. I think that's awesome information. But they will like give you kind of a scale thing, kind of like that over there, and they'll point on there where the temperature of the planet is, which is kind of nice because it puts it in perspective. My problem is that they go, I think it's something like that. Now, does that not just drive you nuts? Negative 300 degrees Celsius. You would never get a minus 300 degrees Celsius because that's colder than absolute 0. And it's on my list of things to do to complain to somebody. I think I should take it to Neil deGrasse Tyson, who got Pluto demoted. If he can get Pluto demoted, he can get this figured out. But anyway, so thank you for listening to me rant. So we have just a couple other topics to cover. If you're looking for a place to live, you might have access to how much am I going to have to run my heater? How much am I going to have to run my heater? That's what heating degree days are. Okay, so what they do is they basically, I don't know about you, but I'm not sure I really set my heater thermostat at 65. It kind of depends on the house. Okay, but let's just say you set it to kick on at 65 degrees Fahrenheit. So what they do is they take all of the days that are, how does this work? Like, for instance, if one day the climate temperature is 30 Fahrenheit, like below freezing, 30 Fahrenheit, what they would do for that day is they would take 65 minus 30, they would add 35 units, 35 cooling units, or heating, yeah, they would add it, how do you have to turn on your heater? 35 units. Okay, that's climate data. And they would do that for each day of the year, 365 days of the year. They use climate data to see how close you are. Well, actually, I guess it would just be in the wintertime. Okay, for turning your heater on. Okay, so look how much, for instance, then, that Anchorage needs to turn their heater on. 10,470 heating degree days, which really it's just kind of like units accumulated throughout the year that are colder than 65. okay? If we compare that to Phoenix, well, Phoenix, Miami, you're like, dude, really? I don't think they need heaters, quite frankly. So turning your air conditioner on is the same thing. It's 65 degrees Fahrenheit, setting your air conditioner to kick on. And then in this case, how many days above that? So for instance, if you had a day that was 85 degrees Fahrenheit, well, minus 65, that would mean that you would add 20 units on for that day. And you would do that for each day of the year. So let's compare that now, like to Anchorage. How much do they need to turn on their AC? Okay, not very much. And let's compare that to Miami. Ha! Take that. So that's kind of how that works. All right. So the last thing in this chapter is if you're doing your weather logs, okay? No, you aren't putting this on, are you? No. This isn't a column, is it? Because you've been doing your weather log. There's no column that says feels like temperature, is there? No. Mm-hmm. Are you doing a weather log too? Yay. Okay. But it's either wind chill or heat index. Okay. So wind chill in the wintertime, heat index in the summertime. It's the feels like temperature. And we'll kind of talk about each one of them. But a few things for you guys to note is that this feels like temperature only applies to warm-blooded animals. It does not apply to reptiles, as far as I know. Well, we've got a reptile, so that came to mind. It does not apply to, I think, cold-blooded animals. But I know it does not apply to inanimate objects like your car. You know, if they tell you the wind, they tell you it's 10 degrees Fahrenheit out there, 10 degrees, which is pretty darn cold, but the wind is blowing so hard that it's minus 20. Like, oh, not good. But it can happen. You've heard that. Your car still thinks it's, what did I say, 10? Yeah, your car still thinks it's 10. I'll try to convince you of that. Okay, similarly, if it's muggy, right, and your thermometer says it's 85, but you're like, dude, there's so much water vapor in the air. And there's a table here to show you at high humidity conditions that 85 our bodies will really feel like it's 105 if the humidity's high enough. Your car doesn't care, it's still 85. Okay, so that's kind of how that works. So starting with the wind chill, and I think you guys have a homework question coming up about this.
Wait, there was one more.
There was one more.
Okay,
To show. Okay, thanks.
Sorry.
Oh, you're fine. So I kind of, I like to think of the wind chill as kind of doing this. This is my Homer Simpson hand. I think he's got like 3 fingers, or it might even vary. Okay, that's my arm, and that's a hand. I know it doesn't look like it. That's a terrible hand. Okay. Anyway, that's an arm, that's a hand. My thing about it is that basically, we've talked about how heat basically radiates. Okay, so heat is actually radiating from your arm. Okay. And we wear, of course, right now, we're all kind of bundled up. We wear clothes to kind of keep our heat in. But even with clothes, what happens is if you get a strong wind blowing, basically it is going to take this cushion of thermal energy that we're used to having around us. It's like our aura. Okay, it sticks with us, but if the wind blows, the wind whips it downstream. So now instead of having that warm thing that we're used to having, bundled up or otherwise, it's gone, and we have a feels like temperature that's colder than the thermometer's saying. So the way this chart works, and I think it was updated a few years ago, for instance, see there's our Fahrenheit temperatures, that's good. So let's pick on 10 degrees Fahrenheit, which is pretty darn cold. If you have winds that are 40 miles per hour, which is terrible, then you see where they intersect. Your feels like temperature is minus 15. Okay. And the way this goes is, of course, this is very dangerous over here. Okay, this is very bad. They talk about dying of exposure, okay? And exposure really can happen for a few reasons if you're not covered up, okay? Because then you at least have a fighting chance of retaining your own heat. But your extremities are very vulnerable to freezing. Not good. Okay, so switching 6 months from the wind chill, we get the heat index. And yes, in Iowa, we get both of those. And the heat index has to do with humidity. Like, oh my gosh, it's so humid and just feels terrible. And the thing is well, maybe this makes sense. In order for dogs sweat, all warm-blooded animals, I think, sweat. We count on sweating. That's the way warm-blooded animals were made. Sweat actually is a cooling mechanism. And the way sweat is a cooling mechanism is basically, and I'll draw my arm here again, basically if your arm is sweaty, okay, you have perspiration. This is my little puddle of water here. Okay, as you are hot, okay, you perspire, and we are counting on this liquid water, which is right here, evaporating. We are counting on that. As it evaporates, heat is used, or heat is absorbed. Where did the heat come from? Our hot arm. So actually this evaporation right here is what cools us down. Now, if there is already too much, these green things are my water vapor. So I'm showing it under very humid conditions. If there's already a lot of water, gas up here, that kind of shuts down, and we'll talk more about that, that kind of shuts down that evaporation process. Under humid conditions, evaporation slows. Put another way is, you guys know if you leave out a bowl of water, for a while, that liquid water is going to evaporate. Well, if it's very humid in that house or whatever, it won't evaporate very quickly. If your house is dry, it's going to evaporate quickly. It's kind of the same thing. So here is the chart for that then. So what you do along the top up here, wait a minute, I guess I should see it around here. What you do in this one is you take the air temperature. So for instance, I said, let's just say it was 84, okay? Let's say the relative humidity is 75%, just dripping, okay? So where they intersect is what the feels like temperature is. So it feels like it's 92. Again, your car thinks it's 84, but you literally feel, I mean, the problem too is we can get into some danger zones very quickly, you know, where literally you won't function correctly. Like, I don't need that going against me, okay? So let me pull up the homework that's due. We'll take a real quick look and then we'll turn you loose. So this homework will be due, and let's see, I think it's this one. So actually, where it says page 94, I've already looked. It's not page 94.
Yeah, I saw that. I looked it up earlier. It's like 87, I think.
87, thank you. And the range probably
86, 87.
86, 87, perfect. Thank you. So it's 86, 87.
I was going to ask you about that.
So not 94, page 86 through 87. And you guys look like you're finding the two sections. I really think on your exams, I might be able to kind of throw some graphs because you're kind of interpreting them for your homework. So question number 2, and the other thing I want to kind of look at with you is I want to make sure I put the asterisks next to ones that you should just be able to answer. Remember, if it has an asterisk, then you don't have to write complete sentences. So this first one, it says the company graph shows monthly temperatures of a couple of locations, similar latitudes, but you can see that from the climatogram that they're different. Which line represents Urbana? And now that needs a complete sentence. because you need to say how you figured it out. Okay, so one line is San Francisco, and one line, which would be, I think, Maritime, and then one line is Continental. So I think you guys can do that. It'd be fun. Number 3, on which summer day would you expect the greatest temperature range? Which would have the smallest temperature range? Explain the choices. Again, a complete sentence. It has to do with, we talked about clouds and no clouds. The next one looks like this. Oops. You're going to use this thermograph. That's an interesting word. It makes sense. This is what basically Peoria through a series of several days. Looks like a week maybe, huh? And determine the maximum minimum temperatures for each day of the week. And then go ahead and calculate from your maximum and minimum, calculate the average. Remember, anytime you see daily mean, that means average. AVG for average, and the range. So I don't think, see, actually I had an asterisk there, so no complete sentences for that one. This one, does this look familiar? This is kind of a fun one. Giving you a couple sets of the real temperature and the wind speed. You're supposed to knock out the wind chill temperature. That shouldn't be too bad. That's number 5, and no complete sentences needed for that one. And then this one, I also have an asterisk, no complete sentences. It gives the average temperature, and then it says the following day the average drops to 45. So this is where, remember what we just did? We calculated the heating degree days, and you're going to compare that to what? 65, right? You're going to compare this to 65 and this to 65. Let's see. Calculate the number of heating degree days. That's cool. How much more fuel would be needed to heat on the second day compared with the first? I don't know. Just do your best. You can BS your way through that one. Okay. All right. Cool. Well, that's all I got. I'm getting out early again today. So we'll definitely start on Chapter 4, which is Unit 2, even before you take your Unit 1 exam, okay? Let me know if you have any questions.
When is the unit?